Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, Ricardo Lopes, and today I'm joined by Dr. Caleb Scharf. He is the director of astrobiology at Columbia University. He works in the fields of exoplanetary science and astrobiology and writes extensively about science for a popular audience. One ultimate goal of his research is to find planets that could harbor recognizable life and to detect the presence of that life. So, Dr. Scharf, thank you a lot for taking the time to come on the show. It's a pleasure to have you on.
No, my pleasure to be here.
Okay, so today we're going to talk about astrobiology and how we can detect life in other planets, because that's what the discipline deals with. When did astrobiology start?
It's an interesting question, and in some respects, astrobiology has been around for thousands of years. I think clearly humans have questioned their place in the universe for a very, very long time, and even speculated about whether or not there's other forms of life elsewhere. Clearly, throughout history, our perception of what elsewhere means has changed as well. What other realities, other planets, other stars, all of that landscape has developed over time. But modern astrobiology, really the modern quest to determine whether or not we're alone in the universe and where we come from, I would say started sometime around the time of the launch of Sputnik in the late 1950s, because it was at that point that a lot of people realized that this question of life elsewhere wasn't just an abstract philosophical one, it was a very immediate practical one. People literally wondered whether by sending spacecraft into our solar system, we were either going to encounter other life directly or inadvertently bring some of it back in the form of microbes. And in fact, that idea of microbial contamination was absolutely at the forefront of what stimulated people to start thinking really scientifically about looking for life in the universe. How do we protect ourselves, but also how do we tread carefully?
Yeah, so I mean, until last century, when astrobiology officially started as a discipline, was it really that respectable for people to speculate about life on other planets? Because if I'm not mistaken, I mean, the sense that I get is that before the discipline officially developed, I mean, people talking about life on other planets, probably most people would look at them as crazy or something like that. Am I right?
In many respects, yes. And it's kind of, again, there's a fascinating history here. If you go back further, maybe 2 or 3 centuries to scientific thought in Western Europe, the idea of life elsewhere wasn't really seen as so crazy. It was kind of it was a topic of speculation, and it seemed more natural that there might be life on Mars or Venus or all these other places than not. In other words, there was a sense of life as just a universal phenomenon. But I think as we got better with our telescopes, as we began to learn more about what was in our own solar system, it became clearer and clearer that there were no obvious signs of other life. There wasn't a civilization on Mars, right, which was a popular idea at the beginning of the 20th century. And so for a while, certainly for the bulk of the 20th century, it's absolutely true. As a scientific topic, it was not exactly fringe, but it was people would kind of shrug. It's like, well, why are you thinking about this? We don't know. We may never know. And that changed, though, I think, in the 1980s, 1990s, and certainly now in the 21st century, from a combination of our ability to explore the solar system and actually answer scientific questions about whether or not life has existed elsewhere in our solar system or exists now. And then, of course, the discovery of planets around other stars has been a remarkable thing. So it's gone from barely respectable to much more respectable these days.
Yeah, that's really interesting. And in astrobiology, you work a lot with a concept that is the concept of habitable zone. So, what are the sorts of traits that characterize this habitable zone, and is it basically trying to compare other solar systems, for example, with the conditions that we find here on Earth? Is that it?
In essence, that is it. So the concept of a habitable zone is a tricky one.
Yeah,
On the one hand, it's a very useful gauge
yeah.
that we use to evaluate environments that we find both here on Earth and elsewhere, and ask, in a very broad sense, is it possible for life as we understand it to exist in this environment? So, strictly speaking, in modern astrobiology, when we talk about a habitable zone, in general, what we mean is actually a range of distances that a planet can be from its parent star,
Uh-huh.
where the surface conditions of that planet, the temperature in particular, if it's an Earth analog planet, so if it's a rocky world with an atmosphere like ours, where the range of temperatures are basically between the freezing and boiling point of water. So the motivation for that as a gauge is that water, as we know, is essential for biochemistry on Earth. It's this extraordinary solvent. It's intimately related to the nature of life's chemistry as we know it. But it also, water is an integral part of the systems of stability and climate on a planet like the Earth. Liquid water plays an essential role in stabilizing climatic change, modifying the surface environment of a planet. So in a nutshell, the definition most of us use is a sort of combined astrophysical definition with this very basic idea of wanting liquid water to exist on a planet.
And with the discovery of organisms like extremophiles, that is, those sorts of, for example, bacteria that live in what we consider to be extreme conditions and that before we wouldn't expect to find them there, is it the case that what we call the habitable zone, or the planets that we would expect to harbor life, increase in number? Because I mean, perhaps there are certain conditions that we aren't expecting to find life in, but it could be there, right?
Absolutely. So the definition I just gave you of this habitable zone is very, very crude and very simplistic. And as you suggest, in the last really 30 to 40 years here on Earth, we've learned that there is more and more life right here under our noses that
Yeah.
is perfectly happy in conditions that for a human are very difficult. And we call them extremophiles. So, for example, there are bacteria and this other single-celled organism form of life called archaea that are perfectly happy living in essentially pools of sulfuric acid in volcanic environments, or at extreme pressures and extreme temperatures deep in the oceans. Even within us, in our digestive system, there are extremophile organisms living in the acidic conditions inside our stomachs. And we've also found organisms that are very resilient against radiation, very good at not requiring very much water, and so on. And that has expanded our viewpoint. You know, we call these organisms extremophiles, but to them, we are the extremophiles. It's not that they're suffering in these conditions, they're thriving. They're perfectly happy in environments that are unusual to us, but are present on the Earth and potentially exist elsewhere in the solar system. So that is one thing that has expanded our view of what a habitable zone might be. Maybe it is hotter than we think it has to be. Maybe it doesn't require as much water. But it's also made us realize that there are environments in our solar system. So, for example, the icy moons of the giant planets, like Europa around Jupiter, we think harbors an interior ocean of salty water. But it's an ocean completely shut away from sunlight. And I think in the past we would have thought that would be a very uninhabitable place. But now we know that there are certainly organisms on Earth that would be, in principle, perfectly happy living in that environment. So, yes, we have expanded our view of where life might exist, not just exist, but actually thrive elsewhere.
I'm not sure if what I'm about to say is correct, but I guess that we also have to take into account perhaps the conditions where life developed on Earth that were not the same as we find them today. Because, I mean, from our point of view, at least, I guess that when we look back at the origins of life, I mean, it developed in an Earth that was much more extreme than it is nowadays. And even, for example, it took a while for the atmospheric oxygen to rise in terms of its levels and to, for example, life on outside of seas and oceans to develop, right?
Yes, absolutely. So, the fascinating thing is that Earth that we see today, the Earth that we love, the Earth with nice beaches and temperate zones and rainfall and so on, and an atmosphere full of oxygen, is just one version of the Earth. If you look back across the last 4.5 billion years, you would see, in effect, alien worlds. From our perspective, Earth has been very, very, very different at different times in history. And certainly in its very youngest time, back 4.5 billion years ago, we think Earth was a radically different environment. The oceans would have been full of iron and nickel compounds. There would not have been oxygen in the atmosphere, at least not in any great quantity. There may have been more extreme variations in temperature. The Earth may have been much warmer at times because of the atmospheric chemistry, and then much colder at times because of that atmospheric chemistry. So this question of the conditions that gave rise to life on Earth is really at the forefront of inquiry. We don't actually have a good answer for what it was that triggered life on Earth. We even don't really have good, completely satisfying scientific definitions of what life is. We actually still struggle with that question. I think one thing we do understand is that for life, or the phenomena that we call life, to have started on Earth, there had to be environments with a certain amount of available energy, perhaps in form of chemistry or in terms of solar radiation. There also had to be conditions that were stable enough to enable complex structures to form. And to go with that in the recipe, there had to have been something to make complex structures. Now, on Earth, we assume, because of what we're built out of, that was carbon chemistry. Carbon chemistry is extraordinarily diverse and versatile just because of the nature of the carbon atom and its bonds with other elements. But there are interesting open questions about whether you could build living systems with other building blocks, as long as those building blocks have this capacity to create ever-increasing complexity. So a lot of the work that's going into understanding both the history of Earth's environment through time and whether or not there were certain times that were better for initiating this thing we call life or not, that's all still very much at the frontier. We don't have complete answers for any of it.
And I guess that not only that, but also the fact that there's good evidence. I'm not sure if that hypothesis is already a theory, has been already proven empirically, but there's good evidence that some of the ingredients that gave rise to life on Earth came from outside. brought in by, for example, an asteroid or a meteorite or something like that, correct?
This is a very interesting question. What gave rise to that starter mix? So if we
Yeah.
assume that there was something just prior to the first living systems or complex chemical systems that we would consider to be life, this question of where did the original mix come from is really interesting. And yes, one possibility is that a certain amount of complex organic chemistry was supplied from outside the Earth. So as the Earth was assembling, certainly 4 billion years ago, it was subject to many more collisions from asteroids and meteorites. The solar system was sort of settling itself down. I always like to say that today we're living in a fossil. We're really living in a fossil system. The most interesting stuff happened 4.5 billion years ago with the assembly of the sun, with the assembly of the planets through gravity and other physics. We know if we look out in both our own solar system and the universe at large that there's chemistry out there, chemistry that actually takes place not on the surface of any planet, but in interstellar space. It can take a very long time for molecules to form. The conditions are cold. The material, the gas, for example, in nebula, the great molecular clouds in our galaxy is very tenuous. But chemistry happens there. And we have measurements that suggest that something like 70 to 80% of all the molecules that are floating around in space are carbon-based. And many of those end up in material that we see as asteroids or meteorites, and that will inevitably rain down on planets like the Earth, like Mars, presumably Venus as well. And so this question of whether you have a different chemical toolkit that then rains down on a young planet and seeds it or initiates life is a really interesting one. And we don't know the complete answer to that, but many researchers have proposed that you needed that catalytic input. You needed that mix of organic chemistry and other elements as well raining down on Earth 4.5 billion years ago to kind of kickstart things.
Yeah, on the other hand, there are also people that propose that we didn't need any ingredients that came from outside and that life basically originated on hydrothermal vents at the bottom of the ocean, correct?
That's right. So, there's division amongst scientists in terms of, the requirements for life and what the secret ingredient. I mean, I shouldn't say secret ingredient. It's nothing secret. Nature isn't secret. It's just we're too stupid to find out what the answer is. Yes, so there are also environments that we see today on Earth that must have existed 4.5 billion years ago. You mentioned the hydrothermal systems. These are in the deep ocean. They're essentially volcanic systems. It's the interface between the Earth's crust and the ocean, and they're chemically rich environments. Some researchers have speculated that there are unique things about the chemistry in these hydrothermal systems. Water is being essentially pumped through hot rock, becoming chemically enriched, and that within those systems, within those rock water systems, there could be sort of little incubators, almost like little test tubes, where you're circulating a rich chemical mixture, you're warming it, it's cooling, it's getting recycled. That could, in principle, serve as a chemical reactor to produce ever more complex chemistry, and even things like, this is quite technical, but lipids, making little sort of protocellular bubbles, essentially gluing molecules together in little spherical spheres with space inside to further trap organic chemistry, to give it a chance to undergo complex reactions. And one of the challenges with any version of how life got going on Earth is how you bring all the pieces together for long enough for interesting things to happen. So the early Earth, like today, had a big ocean. And the big ocean dilutes things. And so there is a dilution question of how do you overcome the fact that, yes, you may have all of these great molecules, but getting them in one place to do interesting chemistry is difficult. So hydrothermal systems are one option. Another option is that when asteroids or meteorites come in, they trigger localized chemistry.
Mhm. And that's very interesting because that gives us a new perspective on how, let's say, life interacts with rocks and with water. Because, I mean, until recently, I guess we had this view that there were different, let's say, domains on Earth, like the geosphere, the hydrosphere, the biosphere, and they were sort of encapsulated or something like that, but now we know that there's a much closer relationship between the evolution of life on Earth and the sort of rocks and the conditions that we encountered on water or in water in this case for life to develop, and there was a relationship, a closer relationship between them, right?
Yes, absolutely. In fact, I mean, today there are new disciplines. There's biogeochemistry
Yeah.
is a field of research, and it deals with precisely that interface. And it's not even an interface; it's an intimate, entwined relationship between living things and the non-biological environment. And of course, what we've also learned is it doesn't just happen on localized scales; it's a global phenomenon. I think we've become increasingly aware of this because of climate change and the change in our atmospheric composition because of human activity. That is one example of this connection. But at a more primordial level, yes, there are microbes that exist within rock. There are even isolated organisms whose metabolic cycle involves making use of water molecules that have been split apart by natural radioactivity in rocks. There's an extraordinary intermingling of non-biological and biological chemistry, which we really hadn't understood before. And it's part of that that has reworked Earth's environment again and again over time. It wasn't just the oxygenation of the atmosphere because of photosynthetic organisms. There was already life manipulating the environment, extracting chemical energy. So this is an area that I think half a century ago we weren't really dealing with. It's now at the forefront, and in particular when we go and look at places like Mars. One of the things that we've discovered on Mars is environments that, or the remains of environments that look an awful lot like they used to be hydrothermal environments like we find on Earth. And therefore, those places are prime targets to look for evidence of past life on Mars or even present life.
By the way, does Mars still have water or not?
It appears to. So actually, very, very recently, even just a few days ago, there was the announcement of some results using radar imaging of the Martian polar regions that suggest great subterranean lakes of liquid water, of salty liquid water. Now, we knew that there was frozen water beneath the surface of Mars, specifically towards the polar regions, which at the moment are cooler on Mars. So Mars actually has a lot of water. It's just, it seems to be beneath the surface and either frozen or now possibly in the form of these subterranean lakes, if you will, similar to the kind of lakes that we see in places like Antarctica, which is truly extraordinary because those places, certainly on Earth, are potential habitats for extreme organisms. And so whether or not Mars still has extreme organisms, we don't know. But there's plenty of water on Mars. If you thawed out all the water on Mars, you would cover the planet in sort of 10, 20 meters of water. But it is mostly beneath the surface.
So before moving on to other questions, let's go back a little bit to the habitable zone. And I've already asked you about the what characterizes roughly speaking, the habitable zone. Is there a minimum set of conditions that a particular planet has to have to harbor life, or to life to originate there, or something like that? I mean, because I would imagine that water would be one of those conditions, the presence of liquid water, and probably, I mean, life has to be carbon based, or not.
Maybe. Yeah, so we end up having to make a lot of assumptions, um, not because we necessarily think those are the only options, but in order to have a chance of recognizing the existence of life elsewhere, which is really the ultimate goal here, is to find recognizable evidence of life elsewhere, whether in our solar system or further afield. So to do that, we necessarily have to use the template we understand. And that involves liquid water, as you say, it involves carbon chemistry, and so on. Based on those criteria, it's still very difficult to point to an environment and say, yes, that has everything necessary, or it has the bare minimum necessary. What we can do is look at environments and eliminate them completely. So, for example, a planet that has molten iron on its surface, we suspect is not going to be capable of either initiating or supporting life as we know it. Equally, a planet or a place so cold that everything, including gases like nitrogen and carbon dioxide, are frozen on the surface seems like an unlikely environment. But all of this hinges on these assumptions that the chemistry that makes us is the universal toolkit for life anywhere. And that seems like a reasonable assumption, at least as a first pass. But the interesting thing is we don't really know whether or not even the details of DNA and the details of the molecular machinery surrounding DNA, is that really the only way to do this, even with just carbon chemistry? So I think there are many unanswered questions about exactly what you need to get life going.
What do you think about that recent discovery of phosphine on Venus? Because I mean, one of the hypotheses there is that it's a molecule produced by some strains of bacteria, right? At least I guess that here on Earth it is the case that some of them produce phosphine. So in Venus it could be the same way.
This is quite an interesting question. So this detection or claimed detection of phosphine in the atmosphere of Venus is very, very interesting.
Yeah.
It's stimulating a lot of work, and there are many questions to follow up. It's difficult though. So to address the specific comment you made, that we think on Earth phosphine is something that life produces. You find it in swamps, you find it around sewage plants. It's one of those byproducts of organic decay. The interesting thing is we actually don't know. If you talk to microbiologists about this, we do not actually know the precise mechanism by which living things make phosphine. In fact, we don't know for sure whether or not it's a direct byproduct of metabolism in a cell, or whether it's some sort of secondary chemistry that happens as organisms dump other compounds into the environment, which is curious to me. So I think my perspective, being very conservative about this, is that it would, we have to be super cautious before we jump to any conclusions about what the presence of phosphine in the atmosphere of Venus would mean. It would be wonderful, if it was indeed the signature of living things. But criticisms of this would be, first of all, that we don't actually understand the origin of phosphine on Earth completely. It seems associated with life, but we don't know the exact biochemical mechanism, which is actually unusual. I mean, we know the biochemical mechanism for many things, how oxygen is produced, and methane is produced, and so on. Phosphine, we don't really know. The second issue is we actually have a very incomplete understanding of the chemistry going on in Venus's atmosphere anyway.
Mm-hmm.
So to see a compound that we don't expect may also be just telling us that we don't have a good scientific picture of the chemistry taking place with or without living things there. So it's going to be interesting to see what happens with this question. With any luck, it will stimulate, if nothing else, new space missions to actually go to Venus and sample things directly, because in the end, that's the only way to find convincing evidence for or against the presence of organisms anywhere.
Mm-hmm. Yeah, and that would be really necessary to prove the existence of life on Venus. I mean, we would have to have space missions to Venus to perhaps collect some direct evidence of it.
Yes, I think so. It's a little sad to have to admit that because so many of us in this field, we spend a lot of time working on how to make remote detections, how to find evidence from across distances that we'll never be able to travel. And in the end, the only truly irrefutable proof, I think, will be either finding microbes directly on Mars or in the atmosphere of Venus, or if some species out there actually talks to us.
Yeah, okay, so we will talk about that in a minute. But before that, are there any biomarkers, let's say, that we can find on other planets without having to go there that would definitely prove the presence of life there?
Yes and no.
Okay.
There are certainly biomarkers that would strongly suggest the presence of life. So things like oxygen in an atmosphere, methane in an atmosphere, even water and carbon dioxide, certain sulfur compounds. A lot of work has gone into this question in recent years of these so-called chemical biosignatures, things that you could detect using telescopes, looking at spectroscopy of light being filtered through a planetary atmosphere or being emitted by a planet, can identify specific molecules that are in that environment. And we think that there are certain combinations of those molecules that could be a fingerprint to tell us that life is there. The challenge is there are so many other ways to produce some of these compounds without life. And that is really, again, at the frontier of research into this, is trying to understand how to discriminate. And so it's not just measuring the chemicals, it's going to be a question of measuring the temperature of a planet, understanding whether it has seasons or not, whether there are dynamic changes. So on Earth, our biosphere reacts strongly to seasonal change. And it does that in ways that are different than a non-biological system. So it may be a question of monitoring these different worlds for years before we can truly convince ourselves that the only thing that makes sense in what we're seeing in the chemical mix and the changes with season would have to be a biosphere, would have to be a planet rich with life reacting to its environmental conditions. So it's absolutely a frontier question, and I don't think we have the final answer on how to do it yet, but maybe we're getting a bit closer.
Mm-hmm. So, in terms of our solar system, what are the best bets, like, for example, planets or moons, where we are expected to find life on?
I think there's a range, and depends on who you talk to as a scientist. So personally, I think two of the environments that are absolutely prime would actually not be planets.
Yeah.
They would be moons. So Europa around Jupiter and Enceladus around Saturn.
Yeah.
These are both places where we are 99.9% sure that there are internal oceans of liquid water. That water is salty, which means it is in contact with rock. It also suggests there's evidence, certainly for Enceladus, that it has hydrothermal systems deep inside. And those oceans are large. On Europa, that ocean, that internal dark ocean, is twice the volume of all of Earth's oceans. So, to my mind, they're different kinds of environments than the Earth, but they are prime places for life to exist. All the ingredients are there that we know existed on the Earth 4.5 billion years ago. They seem like a really good bet. I would also say that Mars is still a really good bet. We tend to think that we've sort of done our exploration of Mars, but of course we haven't. We've landed in a few tiny places, and even with our rovers, we've not really gone very far. And typically we have landed in places that are in some ways less interesting from the point of view of life. And we've done that deliberately because we don't want to contaminate pristine environments that we're trying to study. But that's a double-edged sword. It means you don't land in the places that might give you the best chance of actually finding life. But we're getting there. We're getting closer and closer. The latest missions to Mars, the Perseverance rover from NASA, will do more extensive chemical analysis and so on. And Mars probably, well, we think Mars was more like the Earth a long time ago. Yeah. It may never have been exactly like the Earth. It may always have been a bit colder and a bit drier, but there's extensive evidence that it had liquid water on the surface 3 to 4 billion years ago. It is entirely possible, I think, that there is still life on Mars, if it ever existed there. The interesting question there, though, is whether that life is related to us or not. So Earth and Mars have exchanged material for a very long time. Every time an asteroid hits either planet, pieces of material are thrown into space. We find pieces of Mars here on Earth as Martian meteorites. It's absolutely certain that there are pieces of the Earth on Mars. So there's been exchange of material and possibly the exchange of microorganisms. So a fascinating question will be whether or not we're related.
Yeah, so you touched there on the point that I would like to ask you more about. When you said that we have to be careful about possibly contaminating other planets or moons if we send space missions there to collect evidence for life, for example, because that's a risk, right? At least on Earth. I mean, any kind of surface is contaminated, let's say, with germs, with bacteria. So it's really, or it would be really hard for us to send a space mission to Europa or Enceladus or Mars, for example, and to not contaminate those environments, right?
Absolutely. It's an enormous challenge. And the more we learn about life on Earth, the bigger that challenge becomes, because we learn about extreme organisms. In recent years, it's been discovered that in the world's spacecraft clean rooms, these enormous rooms where a spacecraft is sterilized and cleaned and prepared for launch, that actually those environments exert a Darwinian selective pressure on the microbes, such that in fact there are certain species that thrive in those precise environments because all their competition has been killed off because of the sterilization process, but they're resilient to typical sterilization procedures. So we know already that we have carried microbes to places like Mars. And there are two issues here. One is the desire not to ruin any other ecosystems out there. So it's almost a sort of moral imperative to not do that. Places like Europa and Enceladus perhaps are even more pristine because of their nature being trapped under a sheet of ice. They may never have been contaminated in the history of the solar system. So we don't want to show up and contaminate. But it's also a question of confusing our scientific experiments. You don't want to go to Mars, run a beautiful DNA experiment, discover DNA on Mars, and then later realize it's actually from us. The issue of contaminating your own data is very real and a very difficult one to get around. It's not quite clear how we're going to circumvent this challenge. And of course, putting humans on Mars or anywhere else would be disastrous from the point of view of contamination. Humans are pretty dirty.
Yeah, that's for sure.
And so, but at the same time, a human is a remarkable science machine.
Right.
A well-trained geologist or biologist could probably, in a few hours on Mars, do more science than a robot could do in years. So the question is, how do we balance those risks? And I don't know if we quite have the answer yet. We just have to proceed cautiously.
In the solar system, if these places that we talked about harbor life, what is the kind of life or the forms of life that we would expect to find there? I mean, would it be only microscopic life, like bacteria, for example, or is there any possibility of finding more complex life there?
I think our first bet would be microbial life, microscopic life, single-celled organisms for two reasons. One is that here on Earth, those do represent the majority of life in terms of total biomass, in terms of diversity and occupation of the planet. In that sense, microbes are the most successful form of life that we know of. They also tend to span species that are much more resistant to difficult environments, so the extremophiles. And I think that also is suggestive that they're the first things you might find. But then it's also a question of energy and food and what is needed to support more complex life. So organisms like humans and any multicellular life, we're very energy hungry. We're big consumers of energy through a variety of means. And without that, we die. Whereas microbes, bacteria, archaea, are capable of living very, very slowly. A lot of life in the planetary crust, microorganisms have extremely long lifespans. They can get by with extraordinarily low nutrient levels and so on. So in places like Europa or Enceladus, even Mars to some extent, the prediction is that there may not be much energy there for life, certainly chemical energy. It may be life on the slow track. So that also suggests that organisms we should first be looking for are microorganisms. Now, it could be, let's say, on Europa or Enceladus, there are geothermal systems deep inside where there is enough energy for more complex life to have formed. But it may be very, very niche. It may exist in a very localized region, sort of oasis of energy.
Do you think that if we find life on any of these planets or moons, that we could use some of them as sort of natural experiments to know in what direction life on Earth could move due to the Anthropocene and the impact we as humans are having on our planet? I mean, with global warming and things like that, I would imagine that, for example, Mars could be a good example.
Yeah, I think every planet we try to understand, like Mars, we learn something about the principles of things like climate, the principles of the chemical systems at play on a planetary scale, and that informs us about changes happening to the Earth. I don't think there's anywhere else in the solar system that really represents us in the future necessarily. We used to perhaps think that Venus was that, and I think that's perhaps not quite right. Venus and Earth probably started out very, very similar to each other, but things just didn't follow the same trajectory on Venus as they have on the Earth. But that's not quite the same as a future Earth. But having said that, we definitely learn things about what might happen in the future. I think perhaps the most interesting thing, this relates to your question, would be on Mars. If we discover that Mars once had a rich biosphere, but has now dwindled to a minimal biosphere, that could tell us about critical points. If a biosphere, for example, you mentioned the Anthropocene, or if enough organisms become extinct in a short enough period of time and destabilizes something about the biological system, about the biosphere, we might learn about that by looking at a place like Mars. Maybe there have been places in its history where it too destabilized. I suspect the news isn't good, but we might also learn things about what precipitated those destabilizations, and that could be useful for us.
Yeah, very interesting. And in terms of exoplanetology, are there any good candidates outside the solar system that, I mean, due to the conditions that they have, could harbor life or not?
I think it's fair to say right now there's maybe half a dozen exoplanets that we found that might resemble the Earth or have the possibility of resembling some of the conditions that we find on the Earth. So planets similar size to the Earth at a distance from their parent stars, where they could certainly have liquid water if they have atmosphere, if they meet other criteria. So the number is surprisingly low so far. So we've discovered more than 4,000, perhaps 5,000 planets around other stars. We've discovered them using very indirect measurements. So our information about those planets is very, very rudimentary, very crude. We perhaps know their mass, we know how far they are from their star, and so on. But out of all of those, there are maybe half a dozen worlds that have a chance of resembling the Earth, or have a chance of being a habitable world. But at this point, we don't know any more than that.
Mm-hmm. So, what about intelligent life? Because we are already talking about a complex life when we talk about intelligence. I mean, are there any good? I mean, how should I put it? Is it possible that somewhere in the future we could find different forms of intelligent life throughout the universe? I mean, is it something that we should expect to occur frequently or not?
Well, those are big questions. As they say, those are the $64,000 questions, 64,000 euro questions. So there's nothing, I think, yet to suggest that species like us are necessarily unusual. Mm-hmm. We debate this. We talk about, did certain things have to be just right for intelligent life like us or other species? I mean, an elephant is pretty intelligent. It's not technological in the way that we are, but it has sentience, certainly, and it has intelligence. It has perhaps even conscious awareness. I don't think there's anything to say that is so improbable, although that is still debated. What is really interesting, though, is that actually we are very ignorant about what might be out there, because although we think we've been looking and listening for a long time for other intelligences, right? If you go back a couple of centuries, William Herschel was using his telescopes to look at what he thought were living things on the surface of the moon or on Mars. In the 1960s, we had SETI, the search for extraterrestrial intelligence, using radio dishes and so on. I think many of us have a perception that, well, we've listened and we haven't seen anything, so, okay, maybe there isn't much stuff out there. But the truth is, we actually have only scratched the surface. And this is something that has, in the last 3 or 4 years, come back into the scientific interest. There's recognition that actually we haven't looked that hard. And so I would say it is entirely possible that there's lots of technological intelligent life out there. It's also entirely possible that there isn't. We have no good constraints on this either way. But I guess the optimistic thing, from my point of view, because it would be so extraordinarily interesting and world-changing to find other intelligence out there. The optimistic thing is that we can't eliminate the possibility at all. Mm-hmm. There's really nothing to say that it isn't the case that there's lots of intelligent life out there. I feel like I sound like a lawyer. I'm, trying to phrase this very carefully because it is such a contentious issue. And so much has been said that is unsupportable. People have said, oh, there's no other intelligence, or people have said there must be lots of intelligence. And usually that is based on really sort of nothing more than a hunch. So I think what's happening now is we're beginning to properly analyze this. I think people in the 1960s understood this, but then it didn't sort of take root, it didn't catch fire. So we're coming back and we're saying, no, actually, this is a subject worthy of true scientific investigation.
Mm-hmm. So just one final question, because there are people that say this. There are people that think that we're looking for complex life on other planets, and for example, the SETI endeavor to try to find intelligent life out there, that could pose an existential threat to us, because we would basically be indicating to other, for example, civilizations out there that we were here and they could be more technologically, scientifically advanced than us, and then, as happens in some movies, basically try to wipe us out. Do you agree with that?
I don't, but there are sides to that argument that are perhaps worth paying attention to, and I know that Stephen Hawking, when he was alive, would suggest this. And it's not so much that I don't think a highly advanced technological civilization out there, if it learns about us, what does it care? There's nothing that we could possibly have that I think it would be interested in. Even the fact that we have this habitable planet would probably not be of great interest, because it would have identified many, many habitable planets in the universe. If it wanted to go elsewhere, it could do that without destroying existing civilizations. I think the more interesting and potentially difficult question, which I think is what Hawking was really referring to when he talked about these existential threats, is other species that simply don't recognize us as being particularly interesting life, and therefore mark us down as, oh, there's nothing there, we could make use of this planet or occupy it or do something like that. So life with a very different outlook, that for which we are microbes, could be potentially dangerous, right? Because it simply wouldn't understand that we're sentient, intelligent life if it was sufficiently advanced. But to be perfectly honest, even that I think is a stretch. I think it is possible that the distances involved in interstellar travel are sufficiently difficult to overcome that most interstellar travel, if it takes place, is by machines or something that is not biological in the way that we think of biology, because otherwise it's going to be too difficult. And then actually I'm more optimistic that other species out there, one of the things, most central currency, the wealth of our species is our creativity, our ideas, our biochemistry, the experiment of biochemistry that's taken place on Earth for the last 4.5 billion years, all of that is this rich, rich trove of information about how life works, how the universe works. So I'm actually optimistic that intelligent species out there, if they are out there, will be more interested in exchanging information, in gaining from that than anything else. I don't see the advantage of doing anything more than that. It's the cheapest thing to do is to talk, and you learn the most by talking.
Well, I guess that it's also hard for us to not be anthropocentric when we think about potentially other life, complex, intelligent life forms on other planets, at least the ones that could reach our levels of intelligence. Because, I mean, when we think about that, particularly when we look back in history, I mean, there's always people trying to conquer the world and to subjugate other people. So I guess that there's a lot of anthropocentrism going on there.
Absolutely, and that is perhaps one of the greatest challenges, not just for thinking about intelligent life, but just life in general. Is we live in this one single experiment that has taken place over 4.5 billion years, and we really don't know what alternative pathways that could have taken. And the traits, the human traits that we look at, for example, are tendency to conquer each other, to subjugate each other, and so on. We make these assumptions, as you say, that may be a universal trait, but we don't know if that's true or not. We really don't, because it's so impossible to rerun the experiment with different behavioral patterns. I mean, I feel like maybe there are species out there that it would never occur to them. It just doesn't fit in, and to fight with each other or to conquer, because the Darwinian selection processes that have formed them took place in an environment sufficiently different that just wasn't a selective pressure. It just didn't happen that way. And I don't think we know the answer to that. So there may be incredibly peaceful species out there. It seems hard to believe given our current human circumstances, but it may be true.
Yeah. Okay, so Dr. Scharf, let's end the interview here. Just before we go, where can people find you and your work on the internet?
So I have a website, which is www.calebscharf.com. You can also find me on Twitter at Caleb_Scharf. I try to post mostly science comments or exchanges there. And obviously, if you Google me, you'll find material about me. I also write a lot for Scientific American and Nautilus, which is a online science journal. And I also write books. So if you go to Amazon, wherever you are in the world, you can find some of my books.
Okay, so I will be leaving links to all of that in the description box of the interview. And Dr. Scharf, again, it was a real pleasure to have you on the show and to talk to you.
Fantastic to talk to you. Thank you so much.
Hello, everybody. Thank you for watching this interview until the end. I've started this channel back in February 2018 and have been putting out regular interviews with academics and intellectuals from a variety of fields. So, to keep the channel sustainable, I would like to ask you to consider making a pledge on Patreon. I have the link in the description box, or on PayPal. You can also find the links there. And otherwise, and if you like what I'm doing, please share it, leave a like, and hit the subscription button. I would also like to give a huge thank you to my main patrons and supporters on PayPal: Karen Litzke and Blanchett, Peroga Larsen, Lau Guerrero, Francis Ford, Hans Frederick Sunde, Ricardo Vladimiro, Craig Healy, Adam Kessel, Olaf Alex, Jonathan Wiesel, David Diaz, Anian Kata, Jacob Klinkby, Matthew Whittingbird, Arno Wolf, Tim Hollesy, Henry Calenius, John Connors, Paulina Barron, Philip Force Connolly, Jerry Mueller, Herbert Gintis, Rutger Voss, Bo Weingart, Rebecca Neuberger-Goldstein, Dan Demetriou, Robert Rui Inácio, Arthur Coe, Zoop, Marco Neves, Max Bailey, Colin Holbrook, Susan Pinker, Thomas Trumbull, Bernardo Seixas, Paulo Santurbano, Simon Columbus, Jorge Spinha, Phil Kavanagh, Corey Clark, Mark Blythe, Roberto Inguanzo, Michael Stormer, Eric Neumann, Samuel Andreev, Tiago Nunes, Bernard Hughney, Alexander Dunbauer, Omari Hickson, Felicia Stevens, Fergal Cusson, Evan Bodrenko, Al Herzog, Nuno Machado, Don Ross, João Alves da Silva, Jonathan Librant, Oslam Bullitt, Nathan Nguyen, Staten T, Samuel Correa, Eric Hines, Mark Smith, J.W., João Eira, Tom Hummel, David Sloan Wilson, Yacila Deza Araújo, Ethan Solon, Romain Roch, Dmitry Grigoriev, and Diego Londonio Correa. My producers, Isar Webe, Jim Frank, Lucas Stafiniak, Ian Gilligan, Sergio Quadriano, Luís Caetano, Matthew Lavender, Tom Van Egdam, Curtis Dixon, João Linhares, Benedict Mueller, Vega Guidi, Sardus France, and Niruban Balachandran. And my executive producers, Michel Rojewski, Rosie, and James Pratt. Thank you for all.